Okay, friends, we're starting 2.5. This is actually a fairly short section. We're not going to do everything in here because some of these things get to be pretty esoteric, but this is just applications. In this case, they're physics applications of some of the integrals we've been doing. The first one we're going to look at is a linear density function. So if you just imagine you have a rod of some material, and we want to use this lowercase m to indicate mass. And what we can do is we can integrate the length of the rod, so from some x value of a to some x value of b, of this rho x. And the rho, this is the Greek letter rho. So in English, the capital rho just looks like a p. The lowercase one is kind of a weird script p, but that's a rho. And we use that for density in physics. So that's the linear density function. So if you integrate the density over a distance, you get the mass. So that's pretty straightforward. Then we also have a radial density, meaning I have a disk and I want to figure out the disk again with a density function. Because sometimes you can have a material that you can model that changes density through the material. For our purposes, we're not going to get that advanced, but if you take engineering courses and you do any kind of material science, obviously you're going to be using this a lot. So, but for a disk, obviously it would be 2 pi x times rho sub x from the center to the radius would be the way you would do that. And our last one we're going to look at here is just a simple work function. That work is the integral from one distance to another of the force, whatever the force function is. So remember, work is force over a distance. So if we integrate that, the force function, we can get work out of those. So those three formulas are what we're going to use to do our work here. Again, this is pretty plug and play. There's nothing too complicated about this section.